I don't know, because she said it was a certain percent of like green, so I don't know if it's like this is 25% green, so she's saying like 25% or like, I don't think it's it.
I would find it.
Yeah, because I was like, I told her, okay, and I was like, she was like, no, no, everything I needed. But she needs to, but I still want to know. Underwater. At what?
Seems safe. What's the worst that could happen? Yeah, water. I'm just saying waterboard. No, I didn't know what it was.
Okay, so we've discovered that if we excite individual atoms or samples containing only one kind of atom, that they emit light due to excitation of their electrons. And when we try to diffract or refract that light, it does not give us a rainbow. Instead, it gives us line spectra, and that means that the wavelengths, the energies inside the atom are quantized. That means that they have discrete allowable values, but nothing in between. And it turns out that there is a very, very simple relationship that describes what those values are. That the wavelength of the light that is emitted by our atom is equal to, this is just a constant, RH. So that's my wavelength right here. This is the Rydberg constant. He's the guy that did all the work. And it is 1.09 times 10 to the 7 per meter. And N are just whole numbers. N is just a whole number, it's an integer. And we're going to square those numbers, and this is initial and final. Okay, so we find that the relationship of those bands, those lines that are given out in emission spectra, that the wavelength of those lines falls under a really, really simple mathematical explanation, that this is a whole number. Let's have this be 1. If I square it, I get 1. And 1 over 1 is 1. And then I'm going to subtract from that this number. Let's have that number be 2. When n equals 2, the square of 2 is 4. So 1 over the square of 2 is a quarter. And 1 minus a quarter is 3/4. So we get these really simple, very straightforward mathematical outcomes for what on the surface was a very complex matter. And it's because of this. This is what's happening. If I plot energy this way, I'm going to say that my electron is allowed to have this much energy. Now it's also allowed to have this much energy. And if I want to make it go from here to here, I have to put energy in. That's worth hooking it up to the electricity and pumping enough electricity through it so that it excites. So promoting an electron, so the electrons live right here. To promote an electron from this place to that place takes in energy. I'm going to call that excitation. Promoting an electron from a low energy level to a high energy level is called excitation. This place down here at the bottom, where the electron is naturally spending most of its time, that gets to be called the ground state. And then this would be an excited state. And if I give the atom energy, it will promote an electron from a ground state to an excited state. But if I take that energy away, then the electron falls back down. And in doing so, emits the light. So you can promote the electron, but when the electron goes back to its ground state, it has to give that energy back away. And that energy is emitted as a photon of light. What's the opposite of excitation? Turns out that as you go up more and more in energy, these energy levels start to bunch together. And it gives our line spectrum a little bit of something that's characteristic to them. Because I'm allowed to go from here to here. I'm allowed to go from here to here. I'm allowed to go from here to here. And so I see those energies given back out. And then I also see things like I'm allowed to go from here to here. So there's another set of lines that are completely different color in the spectrum that you can sometimes see. So inside the atom, the electrons are allowed to have these energies. They're quantized, and we're going to start to build on that, but we've got a little bit of classical physics to get rid of, and then we're going to start heading into quantum, because now, because that is a rung on a ladder, and that is a rung on a ladder, and your foot cannot be anywhere in between, right? It can only be on this ladder. Because these are quantized, the math that describes how things move on the macroscopic scale in the universe doesn't work for this. This is going to require a completely new type of math. And I'm going to mention a handful of names. I'm going to leave out some great scientists. I'm only going to mention a couple of people. These ones will do for us. The first is de Broglie. Do not pronounce the G. It's Broglie with like a Y. De Broglie gives us the concept of duality, that electrons can be waves and particles, and he thinks at the same time. Maybe at the same time. They absolutely can do both. Now, the more we look, we find out that they don't necessarily do it at the same time. But if we write an experiment that determines where an electron is, and we try and look at it as a particle, then it will not show us wave behavior. And if we write an experiment that says, hey, electron, show me some wave behavior, it does, it will not also simultaneously show us particle behavior. So electrons exhibit wave behavior and also particle behavior. Okay, so that's odd. This is the first time that we've ever seen that, but hey, perhaps it's an object moving just at the boundary of the speed of light, and maybe it can, you know, maybe I can get my head around it. It's all going to go away. De Broglie, in his explanation, his mathematical explanation, talks about momentum. Momentum comes up in the next person as they move this on. But momentum, anyone know what momentum is? That's inertia. If you're watching a football, they always say the momentum has changed. That's nonsense. They're talking about inertia. They should say the inertia has changed. Momentum has.
Do you watch a lot of football?
I watch a lot of football.
Or college football?
College football, not so much NFL.
Football or rugby?
A&M. SEC. SEC West, unfortunately. And they have the toughest schedule on the planet. Momentum is mass times velocity. What does velocity mean?
Meters per second.
Velocity is just speed, but with the direction. So traveling at 70 miles an hour is a speed. Traveling at 70 miles an hour going north is a velocity. De Broglie, if you look at his math, talks about momentum. Werner Heisenberg comes along and says this. He gives us something called the uncertainty principle. That you cannot know an electron's location and momentum at the same time. On the subatomic level, this does not work. On the macroscopic scale, hey, it works just perfectly. I could get a big ramp, and I could put a little toy car at the top of the ramp, and I could watch the car move down the ramp. If I knew the mass of the car, then I would know what its momentum is going down the slope, because I would use a ruler, and I would mark off the gradations of it is traveling at this speed, and it has this mass. I would now know its momentum. And then I could put a gate at the bottom, and I would know its location. I would be able to know all of those things at the same time. With electrons, that's not possible. Here's why. There's the electron. Let's look at it. What are you going to look at the electron with? Your eyes? Is that the answer? All right, let's look at it with our eyes. That's visible light. There's the electron. We can't see it because the visible part of the spectrum uses a wavelength that is far too long for us to be able to see it. So I'll tell you what we'll do. I'll use light with that wavelength. That'll be able to see it. Light at that wavelength is gamma ray. And when the gamma ray, which is a very high energy beam, touches the electron, it moves it. So where is the electron? I don't know, it's not where you think it is because you just moved it. So you cannot construct an experiment that will allow us to see both things that are going on. Heisenberg was the guy who the Nazis entrusted with building the nuclear weapons. He, of course, never did build one. And the rumor is he didn't want to. If you go back and you look at the history of chemistry and physics, at the turn of the century, last century, all the Nobel Prizes go to Germans, some to go to Scandinavians, but it's all that Germanic part of Europe. That's where all the free thinking, out of the box experimentation, I'm prepared to believe that the universe is a completely different place today than it was yesterday thinking. And all that went away. What made it go away? One word. Hitler. Hitler made it, he ruined it. You know, completely disrupted that cycle of science. We don't know where we would have been without it. I think that we probably ended up at the same place anyway, but we had to relocate all of this, all of that scientific mind, all of that knowledge. A lot of it came to the US. The last person that we'll talk about for right now is Schrödinger. Schrödinger has an umlaut over the O in his name, so it's not Schrödinger. And Schrödinger gives us something called the Schrödinger wave equation. And the wave equation is not understood now, was not understood when he wrote it. He famously said about 20, 25 years, maybe more, maybe 40 years into this, if he'd have known it would have caused such a big fuss, he would never have done it. He gives us a calculation, not in the book, not in the book at all. It's mentioned, but it's not done. And what comes out of his wave equation is psi. And psi is what we call a wave function. And if you square the wave function, it gives you a probability of finding the electron. And of course, we performed this mathematical equation in 3 dimensions. We also do it time dependent as well, so we technically do it in 4 dimensions. And this wave function, so everybody's got used to thinking about waves, and maybe the electron is a wave of energy or with this whatever. And Schrödinger says, nope, not at all. Not at all. My math works, my math maps exactly what's going on inside the atom, and this is not a wave of energy. This is a wave of probability. And if a wave of probability doesn't make any sense to you, that's okay, because nobody understood it when he wrote it, and not so many people do now. But it does things like this. There's the nucleus. You put some values of energies that you find experimentally, into the Schrödinger wave equation, and in 3 dimensions, it starts pumping out numbers. And what it's doing is building a probability density of finding the electron. And ultimately it draws a sphere, and the chances of you finding the electron over here are 0. And the chances of you finding the electron at the nucleus is 0. But finding the electron in a sphere just clustered around the nucleus, pretty good. And we can map that, and we can draw these out into 3-dimensional shapes. This one's a sphere. And it turns out that electrons spend their time in orbitals based on the shapes that the mathematics of the wave equation tell us, and that they're similar, but unique. So Schrödinger leads us to shapes of electron orbitals. And we're going to show you 3 types. The s orbital is a sphere. Okay? So draw an x, a y, and a z. Here's the x, there's the y, and there is the z axis. With the nucleus at the origin of those 3 axes, an s orbital is just a sphere. P orbital is kind of a dumbbell shape. We need an X, a Y, and a Z. I'm going to need 3 of these. Draw 2 balloons stuck together, or a figure 8, or a dumbbell, and there is no electron density at the nucleus. These are clouds of electron density. This one, so the top one is an S, this one is a p orbital. But because it's centered on the x-axis, we're going to call that one px, which kind of indicates that there is a py. And that there is a pz. And then there are d orbitals. And the Schrödinger wave equation predicts electron density in the shape of a clover leaf. And on my x, and my y, and my z, I'm going to need 5 of these. Okay. I'm going to draw a four-leaf clover. That four-leaf clover is going to be entirely between the x-axis and the y-axis. Four-leaf clover that does not touch the x, nor does it touch the y. This is called dxy. That's the easy one. It's flat. Now I'm going to draw one that is between the x and the z. The z is the up axis. dxz. Then I'm going to draw one that is between the y-axis and the z-axis. That is the dyz. These three are what we call non-axial orbitals. They do not put their electron density on the axes. The next one puts all of its electron density on the x and on the y. It's right down the line on the x and the y. And this is called d x squared minus y squared. And then that leaves us just one. This looks like a big p orbital centered on the z-axis, but with a life preserver or a donut around its center. And this is the d z squared. So, about 100 years ago, Schrödinger does the work, starts the work. A bit later than that, I think it's in the 20s that it really comes out, that generates the fact that electrons live in spherical orbitals, or these figure 8 orbitals, or these d orbitals that are clover leaves. Should not take too much of a leap of intelligence to see that that was already predicted by the periodic table. Periodic table is broken up into blocks. On the far left is the S block. In the middle, where the transition metals are, is the D block. And then the other part of the main block on the right-hand side is the P block. Now, here's the thing. Each orbital a maximum of 2 electrons. So the value, occupancy of an electronic orbital could be 0, could be 1, or could be 2. Cannot be a fractional number because there's no such thing as half an electron. Cannot be 3, cannot be -1 because you can't have a negative minus of an electron. Okay? So my occupancy of these orbitals is either a 0, a 1, or a 2, and the maximum that you're allowed to put in is 2. From the periodic table, how wide is the S block?
You can go with 7S.
2. The S block is groups 1 and 2. Just group 1 and 2. What happens if you're reading off on a horizontal row called a period? If you're reading off on a period and you move from group 1 to group 2, what's happening to your atom?
Are you keeping the same number of protons?
No. You add a proton. And for every proton that you add, you have to add an electron. So the question is, how many electrons wide is the S block? 2. There are 2 groups. That's 1 per electron. The S block is just a spherical orbital, and it can hold a maximum of 2 electrons. How wide is the P block? 6. 6 atoms wide. Guess what we do at the P block? 2 electrons here. 2 electrons there. 2 electrons there. The P block is 6 electrons wide. As we move across, we are adding protons into the nucleus, and I'm adding a matching number of electrons into the orbitals, and I'm going to fill all of them. And each orbital can hold a maximum of 2 electrons. Therefore, I have space here for 6. How wide is the D block? From scandium to zinc, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc is 10 atoms. 5 orbitals, each with the capacity to hold a maximum of 2 electrons. 2, 4, 6, 8, 10. Periodic table already anticipated this. Didn't tell us anything about shape, but knew that the elements were going to subdivide themselves down this way. Okay. Now it turns out that each electron inside an atom has something unique about it. No 2 electrons are quite the same. But every electron can be described by just 4 variables. So we're going to call those quantum numbers. And it's like assigning a code or an address to the electrons. That just 4 lines of address tells us exactly everything that we need to know about that electron. So we have a code, and it's called quantum numbers. And because they're unique, no two electrons can have all four quantum numbers be the same. Let's look. Okay, so I'm going to have four numbers. Here's what they are. N. These are all lowercase letters. N is the principal quantum number. And it is a determinant of size. N represents size. And N corresponds to the period number on the periodic table. Okay, so what are my possible values for N? Periods are the horizontal rows. Currently we are in our 7th period of the periodic table. We have not discovered anything in period 8 just as yet. Chances are we never will. Okay, so these are going to be whole number values. 1, 2, 3, 4, 5, 6, 7. We're going to spend all our time up here. I'm not going to go delving down into periods 6 and 7. L has a very peculiar name. It's an azimuthal quantum number. And what it does is it dictates shape. L is the number of nodes. Do you understand what a node is? A node is when your value goes to 0. That's a node. It's not immediately apparent now, but it will be in just a couple of minutes when I sketch these out. Okay, L has values that are integer values. We all okay with what an integer is? Whole number. Whole number values that are somewhere between 0 up to n minus 1. All right, so let's work a little bit. When n equals 1, that means the atoms in the first period on the periodic table, that is hydrogen and helium, when n equals 1, what is my value of L?
0.
L is 0. That's all it can be. It's a number that has to be between 0 and n minus 1, and if n is 1, then 1 minus 1 is also 0. When n equals 2, L can have 2 possible values. L could be 0 or 1. When n equals 3, L will have integer values between 0 and n minus 1. So L will have values of 0, 1, or 2. Here's where looking at what the number of nodes is going to mean for us. When L equals 0, you're an s orbit, just a sphere around the origin. There is no node, it's just a ball. When L is 1, you're a p orbital. The p orbital goes to 0 one time. You can put a line through it, like that. That's a node. When L equals 2, this thing has 2 nodes, here and here. When L is 2, you're a d orbital. Okay, when you look at period 1, there are only L equals 0 s orbitals in period 1. When you look at period 2, there are s orbitals and p orbitals. And by the time you get to period 3, you start mixing in the d orbitals. You've got s's, p's, and d's. Don't look so hard because it's not actually in period 3. The d block comes out of sequence. We'll deal with that much, much later. It's an anomaly. We'll deal with it. N, L, M. M is the angular momentum quantum number, or the magnetic quantum number. The magnetic quantum number. And it used to be that it was just called M, and then the fourth one was just called S. But now they have decided to subscript this M subscript L, and the next one, M subscript S. I actually preferred it the old way, where it was that was an M, and the next one that hasn't appeared yet was an S, because now I have to know a subscript. This tells me the number of possible permutations. You know how there was only one type of s orbital, but there were 3 types of p, and there were 5 types of d's? That's what I mean by permutations. Different arrangements. Okay. This is our number of permutations. And M subscript L has values, again, integer values, between negative L through 0 up to positive L. one. When L is 0, ML is 0. When L is 1, ML has values of -1, 0, and +1. That's the difference between there being one type of s orbital and 3 types of p orbital. And when L is 2, ML is -2, -1, 0, +1, and +2. It gives me one type of S. It gives me 3 types of P, and it gives me 5 types of D. And then the last one. The last one used to just be called S, is now called MS, and this is the spin quantum number. And it says electrons can be ML equals +1/2 or -1/2. So every orbital gets to have a possibility of 2 electrons in it. And if you decide that, hey, this type of d orbital, and that can hold 2 electrons, then one of them has to be plus and one of them has to be minus. And when one's plus and one's minus, we call them spin opposed. And that obeys the laws of physics. Okay.
Is that ML? I mean, yeah, is that ML?
Oh, sorry. That's an S, it's an S, it's an S. Don't go out on a mistake. That's an S, thank you. Check Blackboard. I updated a couple of things on Blackboard today. I made the study guide more relevant. I cut out all the chapter 7 questions and put back in chapter 4 questions. And I grayed out the chapter 7 questions that were on the previous year's exam. I have not checked my email. I've done nothing but work.
Okay, so last night it was like 11 o'clock almost.